Delaware Tech, Chemistry 100, Chemistry 110, the pH scale. The pH scale is a scale that helps us measure how acidic a solution is. Low pH, meaning below 7, 0 to 7, would be considered acidic. Medium, 7 itself, right on 7, is called neutral solution. And anything higher than 7, 7 to 14, is called basic or sometimes called alkaline. So shown here is a visual representation of things you might experience in everyday life that have a variety of pHs on the scale from 0 to 14. 7 being neutral, pure water. If it was absolutely pure water and they even removed as many of the ion electrolyte contents of the water, got it as pure as possible, the pH of water would be around 7. pH of water that you might get from your faucet might be as low as 5 or as high as 8, but it's usually around 7. You find on the far end of the scale, the most acidic things are your acids, so battery acid, stomach acid, even citric acid that's in lemons. In fact, the pH meter, the first pH meter that was invented in the early 1930s, was by a man named Arnold Beckman, who started the company Beckman Instruments, which became Beckman Coulter, you may know of. Beckman started that company by creating the first pH meter. And he did that because the lemon growing industry in Southern California needed a way to tell when the lemons were ripe. Lemons, as they ripen, their acids become more sugar, so the acidity goes down over time. And you want to pick them when the acidity is down a little bit, but not too far down that it's overripe. So this allowed the lemon growers to know exactly when to pick their lemons. And he ended up becoming a very wealthy man starting this company. Sodas have carbonic acid and phosphoric acid, so they tend to be low in pH, somewhere between 2 and 3, depending on which soda you have. Tomatoes are a little bit acidic, coffee is a little bit acidic, milk is a tiny bit acidic. And then once you go into the basic region, the alkaline region, you have things like blood. Now, blood is listed here as 8, but the fact is blood is pretty close to 7.4 pH. In fact, your body goes to great troubles to maintain your blood pH at as close to 7.4 as possible, never going lower than 1/10 of a pH unit or higher than 1/10 of a pH unit beyond 7.4. So your blood is always typically within 7.35 and 7.45, so even less than 1/10. So it's very important to keep it in. If your blood was actually at 8, you would be dead or close to dead. Egg whites, starting to get a little basic because of some of the proteins in the egg white, the albumin. Stomach tablets to help with excess acid in your stomach tend to be basic. They used to be much more basic, maybe 10. Now they tend to be a little less basic because they use weak bases, which don't raise your pH too much unless you need it because acid is being produced in your stomach. Ammonia solutions can be quite basic, a pH of about 10 or 11, even 12, depending on what you've got in there. Soaps can be quite alkaline, basic, though some soaps nowadays have things in them called buffers to keep the pH a little bit lower so it's not so harsh on your body or your hair. Bleach is quite alkaline, quite basic, and you do need to be careful. Bleach is a strong oxidizer, but it's also very, very alkaline and can do damage to your body. Drain cleaners are some of the most alkaline substances you'll be experiencing. They're made with lye, and lye used to be the name for potassium hydroxide. We tend to use the word lye to mean sodium hydroxide, but they're metal hydroxides, alkali metal hydroxides that are all known to be quite strong bases. So, what is pH? Well, pH is actually the result of a calculation. The P in pH means negative power of 10 of the concentration of the hydrogen ion. So the H in pH refers to the protons being formed by acids, and the P refers to the power of 10 that it is, because the pH scale is a log scale. If you have pH 1, that's 10 times more acidic than pH 2. And the reason why it's reversed is because you see there's a negative sign in this formula. pH is equal to the negative log, and it's a base 10 log, the negative log of the concentration of protons or concentration of hydronium ions. They're really the same thing in water, and that will give you a value. And because of this negative sign flipping, that is why low pH is high acid and high pH is low acid, and high pH also means high base or high alkaline. So, if I take that same first equation here, pH is equal to negative log base 10 of the proton concentration or the hydronium concentration, and I rearrange that equation to get the inverse function, I get that the concentration of our proton or hydronium ion is equal to 10 raised to the minus pH power. So this is why it's the power of. So you see, it's 10 to the power of the negative pH is equal to the proton concentration, hence the term P, hence the part P in pH for the power of the concentration of hydrogen. And we have other P things. We have a POH when we're looking at hydroxide concentrations, and we have a PA when we're looking at the negative log of things like the Ka, the equilibrium constant for acids. But we're not going to talk about the Ka right now. We will be discussing the POH soon. So we have these two formulas for going from pH, the first one is going from our acid concentration to our pH, and the second formulation is going from our pH to our acid concentration. So pH is the negative power of the proton concentration, the hydrogen ion concentration. In an acidic solution, again, that is where the proton or hydronium ion concentration is high. High means greater than 1 times 10 to the minus 7 molar, and pH will be less than 7. And you see those 7s are from each other. In a basic solution, when the proton concentration is low, that means our hydroxide concentration is high. Remember that from before when we were looking at Kw. So low acid concentration means high base concentration. In that case, our pH will be high, greater than 7. And when the two concentrations are equal, the proton or hydronium ion and the hydroxide ion concentration, which is not written here, are both equal to 1 times 10 to the minus 7, well then the pH is exactly 7, and that is called neutral. So here are two problems. If we know the proton concentration, in other words, our acid component of the acid, or also the hydronium ion concentration, is 3.45 times 10 to the minus 6, what's our pH? Well, we plug it into our first equation at the top here. The pH is the negative log of 3.45 times 10 to the minus 6. Now, we don't write the molar in there because pH is a unitless number. There is no unit for pH. pH, some people say, oh, the unit is pH. No, no, no. pH is the parameter you're reading or you're measuring or you're calculating. The unit of pH is nothing at all. So the pH in this case is 5.462. Now, if we start with the pH instead, here's a pH 9.732. We know this is basic, so we know our proton concentration should be low in this case because of the high pH. What is the hydronium ion concentration? That's the same as asking what's the proton concentration. Well, it's equal to 10 raised to the negative power of the pH. So it's 10 to the minus 9.732, which, when you plug that into your calculator, is 1.85 times 10 to the minus 10. Now, make sure you know how to do these calculations in your calculator. Each calculator is different. In some calculators, you would put in the change of sign to create that negative sign first. So you would hit the, so for this one, you would hit the plus minus button on some calculators. Sometimes it says CHS for change sign. Sometimes it's a minus sign in parentheses, but do not use the minus sign, the regular minus sign. Use the change sign. And then you would put in the log button. Sometimes it says log, sometimes it says log base 10. It's not always there, and that would be another button. And then you would put in your number. And this number is in scientific notation, so you'd type in 3.45. Your EE button or EXP button, your change sign button because this is a negative power of 10, and then you'd hit the 6, and then finally equals. If you were to use the times here or the minus sign here instead of using the proper functions, you will not get the correct answer. So make sure that you try this problem and make sure you get this exact answer. And likewise, with the second problem here, example 2, make sure you know how to do this. This is when you finally get to use the 10 to the x button, which might be right on top of your log button. It might be the log button, and then you may see 10 to the x written right above it. But the 10 to the x button is the button you're going to use. So you would, some calculators you put in your number first and then 10 to the x button. Some you put the 10 to the x button in first and then you put your number. And again, this is a negative a negative 9.732. So you would hit this button and then your change sign button, which would look like that. And then you'd put your 9.732 in there and hit your equal sign, and hopefully you get something that looks like that, 1.85 times 10 to the minus 10. Of course, on your calculator, it'll probably look like 1.85, and it might have an E, and then minus 10. That means this. It means the same thing. In some calculators, there is no E showing on the display. It just says 1.5, and then over on the right, it says minus 10. Every calculator is different, so make sure you know how to use your calculator to do this. One more note I want to point out here. You might be saying, hey, this is the wrong number of significant figures. I've got 3 over on my left side. Let me get the right thing here. 3 over here, but I've got 4 over here. And I got 4 over here, but I ended up with 3 over here. Well, pH is a little odd with calculating significant figures. These are significant figures. These are significant figures because they're in scientific notation. All 3 of them are good. In pH, we only count the numbers on the right side of the decimal place for our sig figs. So if somebody gave you this value of pH and they told you it was a pH, you only count these. You don't count anything on the left side of the decimal point. It's just the odd quirk of using powers of 10 and logarithms. So that's just something to point out. So let's look at POH. So this is the same thing as pH, but instead of doing the negative log of the hydrogen ion concentration, the proton concentration, the hydronium ion concentration, now we're doing negative log of the hydroxide concentration. So that's the POH. And the inverse is just like before. The hydroxide concentration is 10 raised to the negative power of the POH. So these are 2 versions of the exact same formula, just written to solve, in one case to solve for the POH, and the other case to solve for the hydroxide. So POH is the negative power of the OH minus concentration. Again, that's where we get the name POH. In an acidic solution, everything is switched that you learn with pH. So acidic solutions, the pH is low, but the POH is high. In a basic solution, the pH is high, but the POH is low. So everything's exactly the opposite of what you might imagine, so it's very easy to confuse these two. And in a neutral solution, it's the same. POH is the same thing as pH, and they're both equal to 7 because both the proton, the hydronium ion concentration, and the hydroxide ion concentration are both exactly equal to this middle number of 1 times 10 to the minus 7 molar. So, pH versus POH. Now, here are a bunch of derivations. You don't need to know the derivation. It's just the end result that's going to be important. But if you like math, here it is. We start with the KW expression. Proton concentration times hydroxide concentration equals 1 times 10 to the minus 14 molar squared. Now, we know that we can take the logarithm of both sides. So we do that. And we also know from using logs, if you remember your logarithm in algebra, that if you have the log of 2 things multiplied by each other, you can separate them into 2 logs that are added to one another. So the log shown here of the proton concentration times the hydronium concentration in brackets and braces here as one thing is the same thing as the log of just this plus the log of just this. Now, you don't need to know any of this math. You don't need to know any of the derivation. This is just for those of you who like it. So we know that we can take the negative of everything. So now we've got that same expression, but every term I've switched to a negative sign. Now I want you to notice this is the definition of pH, and this is the definition of POH. Well, what is this? That is just 14. The log of this would be minus 14. The negative log would be 14. So what this means in the end here is very important. This expression, our KW expression, when rewritten as logs, just tells us that whatever our pH is, our pH plus our POH will always add up to 14. So if somebody tells you the pH, you know the POH. If somebody tells you the POH, you know the pH. It's just they both have to add up to 14, so 14 minus 1 is equal to the other. Just like up here, if you know the proton concentration or the hydroxide concentration, all you have to do is take this number and divide it by either one of these to get the other. So that equation rearranged gives us this bottom equation that is so much simpler to use. So if you have the choice of using one of these two, always go with the bottom one, of course. And so just to review what we've talked about in terms of relative numbers here, we have a pH scale that goes from 0 to 14. 0 is acidic, 14 is very basic, 7 is our center, it's our neutral pH, it's our only neutral pH. And this corresponds to concentrations of protons of our acid. So 0 would be 10 to the 0. 1 would be 10 to the minus 1. It's 1 times this, but I'm leaving out the 1. 1 times 10 to the minus 3 would give us a pH of 3. 1 times 10 to the minus 5 molar, and these are all in molar, by the way, concentrations. So these are all concentrations in molar of our hydrogen ion, our proton, our hydronium ion. They will always correspond as long as it's 1 times this value. If it's not 1 times this value, you have to use your calculator to figure it out. But if it's just 1 times that, you can see the number and go, oh, that's 11. That's pH of 11. So that makes things very simple. Now remember, the POH scale isn't exactly inverted. So a pH of 14 is a POH of 0. And a pH of 0 is a POH of 14. Because they always have to add up to 14. So if I had a pH 3, well, that's going to correspond to a POH of 11, and vice versa. So that's easy. And then going from the POH to the actual OH minus concentration, well, this is always the negative power. It's the negative version of the power of 10 that is in the concentration. So 1 times 10 to the minus 14 molar OH minus corresponds to a POH of 14, but a pH of 0 and a proton concentration of 10 to the 0. And 10 to the 0, by the way, is just 1 molar, so that's very concentrated. You might ask, what happens at higher concentrations than 1 molar? Well, we still call it 0. We just don't call it anything, and we don't use negative numbers usually. Occasionally we will for special calculations, but in general we don't bother. And with that, we'll stop here.